Hello everyone, and welcome to another video on our statistics chapter. Today we're going to do a little overview about frequency distributions when we're talking about the shape of the distribution. So sometimes when we graph our data, it may take on a particular shape, and that particular shape may go into a category as far as a type of distribution that we are seeing. So let me just kind of go into that with an example so you can kind of understand what I'm trying to explain. And then we're going to look at some of the more common distributions that we will see when we graph data. All right, the first one is the rectangular distribution. So for example, let's say you roll a die many times. We would expect the numbers 1 to 6 to occur with about the same frequency, right? Let's go back to probability real quick. When we talked about the probability of rolling a 1, 2, 3, all the way up to 6, they all had the same probability. So then if we're going to be rolling a die many times, we would expect that we're going to see each number about the same amount of frequency. So we would expect to see ones, the same amount that we would see fives, for example. And so what happens is if you look at this graph here, so this is our rectangular distribution, and you can see the shape that it's starting to take. And that shape right here, would that be that of a, well, rectangle, right? Hence the name rectangular distribution. Because this would be, and I'll just kind of pencil this in here. This would be, for example, the frequency that we saw when we rolled ones. How many ones did we get? How many twos did we get? All the way up to how many sixes did we get? And like I said, we would expect to see about the same frequency. And here are your frequencies. So whatever that is, we would expect to see about the same, which would hence give us a rectangular distribution. Here's another one, J-shaped. Now, if you're looking at this, you might think J, but you kind of can see the shape, right? You're starting down here and then you're making, because if you think about a J, at least that's how I look at a J. But that's probably the older J, but you see how we kind of get that shape. You got one going this way, and then if we also have the option of it going the reverse side, it's still taking on this J shape, just more reversed. For example, the number of hours that students might study per week, that could take on a J distribution. And we could also see it going in the reversal. Here's another one. We call this the bimodal distribution. For example, if you have an equal number of men and women were weighed, the distribution of their weights would be bimodal, meaning you would have one mode for the women's weights, and then you would have a second mode for the men's weights. So here you can see right here, this one would be for the women's weights, and then this one here would be the mode for the men's weights, hence bimodal. And so you can see, and you can tell when you look at a graph that that would be that type of distribution that we're seeing. Another one that we tend to see common is skewed distributions. What happens here is you look at this graph, you can see that you have a majority of the frequency occurring within a certain amount, but then you start to see it trail down here. Notice as it's trailing, I'll kind of show you, this is how I kind of show my shape. So I'm just going to draw it real quick. So you tend to see something like this. If I were to draw over these bars, and I tend to see this. This is what we call skewed to the right. Over here, and it's on this graph, and I'll try to draw that one. Again, not very well, but with this one, notice that we're going the other way. And so this one we're calling skewed to the left. All right, and so your example here would be the number of children per family could be skewed to the right. All right. Oops, scrolling the wrong way. Oh, look, I forgot I had the pictures already here. See, those are much neater than what I just drew for you. Okay, so let's just do an example here. Here's a histogram to the right. Now this is showing the times between eruptions of a geyser. Draw a smooth curve that captures its important features, and then classify the distribution according to its number of peaks, symmetry or skewness, and variation. So we're looking here. So here are your options. Now, if you look at this graph up here, hopefully you can see my highlight with my mouse. Notice what the shape is taking. If I were to draw a little curve around here, right, just to kind of show the shape, this is pretty much what I would be drawing. So if I look at the options I have here, which one fits that the best, that would be option B, because notice it's taking that shape that we were able to draw to represent the shape of the bars. All right. Here's another example. So let's consider the distribution of the numbers of people whose street address ends in either a 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So we have 10 values. How many peaks would you expect for the distribution? So again, we're talking about people's addresses who would end in one of these numbers. Now think about that. Every address is pretty much going to end in one of these numbers, right? So really, we wouldn't expect to see any peaks. And I'm just going to write that down. There should be no peaks, because we would expect everybody to have an address that ends in one of those numbers, which means if you don't have any peaks, what would that look like in my crooked graph? We would expect to see more of that rectangular distribution where each of these numbers, and I'm not going to draw all of them, but you can see my point. You would go all the way up from 0 to 9, but we would expect all of them to have an equally likely frequency. 10, actually, we go back to probability, and equal likely probability as well. So would you expect the distribution to be symmetric, left skewed, or right skewed? Well, the distribution would probably be symmetric because there are no obvious factors to indicate that any single digit would occur as the last digit more frequently than another digit. Unless we were given some specific rule for that particular neighborhood, then we would not expect there to be any difference, any likelihood of one occurring more than the other. And so that's why we would expect it to be symmetric. And so for D, would you expect the variation of the distribution to be small, moderate, or large? The variation would we expect to be large because addresses can end in any of those 10 digits. And so we would expect the variation to be large. Now, we're going to get more into variation when we get into the video all about standard deviation, and we'll talk more about variation then. All right, so that ends our video when it comes to shapes of graphs and different types of common distributions that we tend to see in statistics.